Okay, imagine this. You hear about an asteroid, right? A pretty big one. And it's heading towards, well, not us, but our closest neighbor, the moon. So your first thought probably is, okay, dodge that bullet, not our problem. But what if? What if hitting the moon is actually our problem? What if that impact way out there could kick up this cosmic hailstorm? Not hitting our atmosphere necessarily, but hitting where it really counts for us now, our satellites. The thousands of them powering everything from GPS to, well, your internet connection.
It's a really fascinating idea. And yeah, maybe a little bit unnerving when you think about it. It really makes you reconsider how connected everything is up there in space. How something happening far away can have these ripple effects right back here.
Absolutely, and that's exactly what we're getting into today. We're doing a deep dive on Asteroid 2024 YR4. This isn't just some random piece of space rock floating by. This one actually has a significant chance, like not zero, of hitting the moon in 2032. But here's the kicker. This is where it's really interesting, maybe a bit alarming. The potential for that crash on the moon to just unleash the shower of debris, fast debris, straight towards Earth. And that poses this surprising and frankly pretty real threat to all that technology we have orbiting up there.
Right. So our mission for this deep dive is basically to unpack the science behind this whole potential chain of events. We'll look at the asteroid itself, its path, which was already a bit dramatic earlier this year, remember? Then we'll dig into what actually happens during a high-speed lunar impact. The physics are pretty wild. And then the really crucial part, how does that ejected stuff, the lunar material, actually make its way towards Earth? It's not obvious.
Exactly. And while we're following that cosmic story, we'll definitely talk about the real-world implications. What does this mean for our satellites, the ones that run so much of our modern world? And maybe, just maybe, what kind of light show you might actually see from down here on the ground? It's this whole cosmic drama unfolding, but with, like, real tangible stakes for us. Okay, so let's get into it. All right, let's start with the main player here, the cosmic cannonball itself, Asteroid 2024 YR4. And when we say asteroid, we're not talking about, a little pebble. This thing is substantial. Scientists figure it's about 60 meters across. That's roughly 200 feet. Try to picture that. Maybe like a 20-story building or a big sports arena. That's the kind of scale we're dealing with. Some scientists have even described it pretty starkly, saying it's big enough to level a city. Just let that sink in. It's a serious piece of rock.
It is. And that size is exactly why 2024 YR4 caused, well, a bit of a scare earlier this year, a real one. Its initial calculated path raised some pretty serious flags that it might actually hit Earth directly. The probability, I think, was calculated at 3.1%. Now, that might sound small, like in everyday life, but in the world of tracking asteroids, for something that big, that was actually the highest probability ever measured for a potential Earth impact from such a large object. It definitely put people in the planetary defense community on edge for a bit.
Oh, I remember that. Yeah, there was this kind of collective breath holding, wasn't there? And then this huge sigh of relief, not just from us, but from scientists everywhere when those follow-up observations came in. Ground telescopes, and then the really crucial data, I think it was May 2025 from the James Webb Space Telescope. That data definitively ruled out a direct hit on Earth. That was a game changer. Let everyone breathe a bit easier.
Definitely. Earth is safe from a direct hit. But the story didn't quite end there for 2024 YR4. In a sort of unexpected twist, as the Earth impact odds dropped to zero, the chances of it hitting the moon actually went up slightly. The main scientific paper puts the new odds at about 4%, up from 3.8%, though you might see some news articles mention 4.3%, probably just using slightly updated figures or rounding from those same JWST observations. So yeah, somewhere around 4.3% chance of hitting the moon. It's certainly not a guarantee, but it's definitely not negligible either, especially given what we're about to talk about next.
And if it does hit the moon, they've even pinpointed a potential date and time, like down to the day.
They have. The potential impact date is December 22nd, 2032, and the impact velocity. It's just staggering. We're talking 13 kilometers per second.
13 kilometers per second. Okay, wait. That's about 8 miles a second.
Yeah, roughly 8 miles per second, or almost 29,000 miles per hour.
Wow. Okay, that's almost impossible to really visualize. Like LA to New York in, 5 minutes?
Something like that. It's just immense kinetic energy packed into that 60-meter rock.
Okay, so this leads to a waiting period now, right? We can't just keep watching it.
Exactly. That's a crucial point right now. The asteroid 2024 YR4, it's currently too faint, too far away for our telescopes to see it. It's not expected to become visible again until sometime in 2028. So the world, and especially the scientists tracking it, we all have to wait a few years for more precise data on its trajectory. Those future observations will be absolutely key. They'll let us narrow down the orbital uncertainties, maybe use new instruments, and then we should get a much clearer answer on whether a lunar impact is truly likely, and maybe even narrow down where on the moon it might hit. Right now, the predictions are based on the best info we have, but that uncertainty period is a big factor.
Okay, so let's jump ahead. Let's imagine it's December 22nd, 2032, and it happens. The asteroid hits the moon. What are we looking at then? You mentioned a gigantic explosion.
Gigantic is the right word. It would be, well, spectacular from a distance, no doubt, but incredibly violent up close on the lunar surface. The scientific models, the ones that simulate these things, estimate that if 2024 YR4 hits the moon, it would release energy equivalent to about 6.5 megatons of TNT.
6.5 megatons. Okay, how does that compare to something we might, recognize?
Well, think about the atomic bomb dropped on Hiroshima. That was around 15 kilotons of TNT. So
Yeah.
6.5 megatons is, you do in the math quickly,
Mm-hmm.
nearly 430 times more powerful than the Hiroshima bomb. This isn't just a big splash. It's a genuinely monumental event on the moon's surface.
And what would we see? I mean, what kind of mark would that leave?
That energy has to go somewhere. It would carve out a brand new, pretty significant crater. The models predict what's called a transient crater. The initial hole blasted out roughly 1 kilometer in diameter. Now, there's a bit of range there, maybe 0.7 kilometers if it hits really loose lunar soil, the regolith, or up to maybe 1.4 kilometers if it slams into solid bedrock. But because we don't know the exact ground conditions at the impact site, scientists are generally saying on the order of 1 kilometer.
Okay.
So picture a new hole, a kilometer across, gouged into the moon, deep enough to be easily visible from orbit.
A kilometer-wide crater. We see lots of craters on the moon, though. Is that particularly special? How often does something like that happen?
That's a great question. And yes, this would be very special. Very rare, actually. Statistically, a crater that size, 1 kilometer across, only forms on the moon about once every 5,000 years.
5,000 years.
Yeah. Think about what Earth was like 5,000 years ago. Humans were just starting to write things down. The first big cities were popping up in Mesopotamia. The pyramids weren't even built yet. So if this impact happens, it would statistically be the biggest thing to hit the moon in about 5 millennia. It really underscores how unusual and powerful this potential event is, at least within the time scale of human history. A really rare occurrence.
Wow. Okay. So beyond just digging a big hole, the real issue for us back here and for satellites, that's the stuff that gets thrown out, the ejecta.
Ejecta. That's the key concern for Earth orbit. This impact, with all that energy, it would blast out a truly staggering amount of lunar material. The estimates are up to 100 million kilograms.
100 million.
Yeah, kilograms. Yep, that's about 220 million pounds, or, scientifically, 10 to the power of 8 kilograms. And here's the crucial part. A significant fraction of that material gets kicked out so fast that it exceeds the moon's escape velocity, meaning it literally breaks free from the moon's gravity and heads out into space.
Okay, so when we talk about this ejecta, this 100 million kilograms, what is it? Like, are we talking giant moon boulders flying at us or something else?
Mostly, no, not giant boulders. The vast majority of the ejecta traveling at those really high escape velocities would be tiny fragments. Think micron-sized dust, up to maybe millimeter-sized bits. The studies use something called a power law distribution to model this. It's like shattering glass, right? You get maybe 1 or 2 big pieces, but millions of tiny sharp slivers in dust. It's the same idea here. For every relatively large chunk thrown out, there are exponentially more tiny pieces, millimeter-sized, micron-sized, and at the speeds they're traveling, even a tiny speck can pack a serious punch.
Can you give us some numbers? Like, how many pieces are we actually talking about? Because 100 million kilograms is hard to picture as individual fragments.
Sure. The models give some truly mind-boggling numbers. Let's see. They estimate something like 100,000 up to maybe a billion fragments larger than 10 millimeters, so bigger than a marble. Then for fragments larger than 1 millimeter, like grains of sand, maybe small BBs, we're talking somewhere between 100 billion and 10 trillion fragments.
10 trillion.
Yeah. And then down to 100 micrometers, about the width of a human hair, the numbers get astronomical. 10 to the 14 to 10 to the 16 fragments. So while most are tiny, the models do suggest the largest pieces thrown out at escape velocity could be maybe up to a meter across, about 3 feet. But the bulk is really that smaller stuff, down to fine lunar dust. It's this enormous cloud of material across a huge range of sizes, all moving incredibly fast, like cosmic shrapnel.
Okay, an incomprehensible cloud of cosmic shrapnel. That sounds bad. But how does it get here? I mean, the moon's orbiting us, it's moving. The stuff doesn't just fly straight off in all directions and randomly hit Earth, does it? There has to be more to it.
You're absolutely right. It's not random at all. And this gets us to maybe the most critical factor,
Yeah.
where on the moon, the impact happens. The ejecta doesn't just scatter uniformly once it escapes the moon. The fraction of that ejecta cloud that actually ends up reaching Earth,
Hmm.
it's highly, highly sensitive to the impact location. Think of it like hitting a pool ball. The angle is everything for where the other balls go.
So there's like a sweet spot on the moon, a place where an impact is much more likely to send debris our way.
Exactly. There's definitely a sweet spot. The simulations show the highest delivery rates to Earth happen if the asteroid hits the moon's trailing edge. That's the side of the moon facing away from its direction of travel as it orbits Earth.
Okay, why the trailing edge specifically?
It's down to orbital mechanics, actually. Pretty neat, in a way.
Huh.
When material gets ejected from the trailing edge at high speed, its velocity, after escaping the moon's gravity, can effectively cancel out a large part of the moon's own orbital velocity around the Earth. So relative to Earth, this debris suddenly isn't moving very fast sideways anymore. It's almost like it gets left behind by the moon, and then Earth's gravity just pulls it straight in. It basically allows it to fall directly towards our planet. It's a very efficient delivery mechanism.
Huh. Okay, so where is 2024 Wire 4 actually predicted to hit? Is it anywhere near this trailing edge sweet spot?
Well, the predicted impact corridor, the range of possible impact points based on current orbital data, is in the moon's southern hemisphere, roughly between 30 and 40 degrees south latitude. Now, a lot of that corridor, maybe most of it, is actually on the moon's leading side, the side facing forward in its orbit. But there's still about a 14% chance, according to the models, that the impact could occur on that crucial trailing side. 14% might not sound huge, but given the potential consequences, it's definitely a probability we need to take seriously.
Okay, 14% chance of hitting this sweet spot. And if it does hit there, how much of that 100 million kilograms of ejecta actually makes it towards Earth? You mentioned delivery efficiency.
Right. Delivery efficiency is exactly that. What percentage of the total stuff blasted off the moon actually gets aimed towards Earth's vicinity, where our satellites are? And the research shows there's a significant chance tied to that 14% trailing edge probability that 2024 YR4 could hit a part of the moon with a delivery efficiency to Earth greater than 10%. So upwards of 10% of all that ejected material could get funneled our way instead of just flying off into deep space or falling back to the moon, and it would arrive quickly.
Can you give us some examples from the simulations? They use different clones to test impact points, right? What did those show?
Yeah, the study simulated various scenarios using these clones representing different points within that impact corridor. So, for example, they had clone A hitting pretty far east on the moon at about 40.7 degrees east longitude, and clone B closer to the center line, near 1 degree east. Both of those fall within that high-efficiency trailing edge region. And the results. Clone A sends about 11.9% of its ejecta towards Earth. Clone B sends 8.4%, significant percentages. But here's the really striking part, the speed. For clone B, the first bits of debris could start arriving near Earth within just 3 days of the lunar impact.
3 days, that's it.
Yeah, 3 days. For clone A, it was about 5 days. So we're not talking about a slow drift over weeks or months. If it hits that sweet spot, it's a rapid delivery, a cosmic downpour starting very quickly.
Wow, okay. And what if it hits the other side, the leading side or the far side?
Totally different story. They simulated that too, with clone C impacting around 60 degrees west on the leading side and clone D way over on the far side at about 124 degrees west. For those impacts, the delivery efficiency to Earth plummeted, only 0.19% for clone C and a tiny 0.04% for clone D. And the material that did eventually head towards Earth from those impacts would take much, much longer to get here, over 80 days. So it really hammers home how critical that impact location is. That 14% chance of hitting the trailing side makes all the difference.
That really is the key takeaway then. If this thing hits near that eastern edge, that trailing edge, something like 10% of maybe 100 million kilograms of debris, that's still 10 million kilograms, could be heading our way, arriving in just a few days. It's like, years, maybe a decade's worth of normal space dust exposure for satellites, all compressed into one really intense week. That feels like a fundamental shift in thinking about orbital hazards.
It is. And it's not just the amount of material, it's the speed it arrives at. Now, thankfully for us on the ground, the atmosphere does its job. It burns up this stuff. But for satellites up there above the atmosphere, the relative impact speed is what matters. This lunar ejecta would be traveling near Earth's escape velocity when it gets here. That means impact speeds on satellites would range from about 4 up to 18 kilometers per second. For context, the average speed of natural meteoroids hitting Earth's atmosphere is around 20 kilometers per second. So these particles are hitting with speeds very much in the range of the space debris and meteoroids that we already know can damage or destroy spacecraft. They're essentially tiny, high-velocity bullets.
Right. So let's get right into that immediate danger. For our satellites, first, just to be super clear again, people on the ground are safe from the actual particles, right? Our atmosphere handles it.
Yes, absolutely. Earth's atmosphere is an excellent shield against millimeter to centimeter-sized particles like most of this ejecta would be. They'll burn up harmlessly high above us, producing meteors. A potentially great light show, but no direct danger to the surface. Your house, your car, you're safe from these things hitting you.
Okay, good. Phew. But the satellites, they don't have that shield.
Exactly. That's where the real threat lies, our orbital infrastructure. Thousands of satellites, these high-velocity lunar particles, even the ones just millimeters across, hitting at tens of thousands of meters per second. They can act like miniature projectiles. They can easily damage sensitive components, solar panels, antennas, sensors, or if they hit a critical spot, they could potentially disable or even destroy a satellite entirely.
And the number of potential targets up there is just exploding, isn't it? Especially in low Earth orbit, LEO, with things like Starlink and other mega constellations.
Absolutely. That's a critical piece of this puzzle.
Hmm.
The sheer density of our orbital assets is increasing dramatically.
Hmm.
By 2032, the total cross-sectional area of satellites just in LEO is projected to be 3 to 4 times larger than it is now. A huge part of that growth is these mega constellations providing global internet and other services. They'll make up the vast majority of active satellites. All told, we're looking at a total exposed satellite area of something like 100,000 square meters by then.
100,000 square meters. That's like, what, 14 football fields?
Mhm.
Just floating up there as targets?
Pretty much, yeah. It's an enormous collective target area for any incoming debris cloud.
So,
Given that huge target area, what do the models predict in terms of actual impacts? You mentioned fluence. How many hits per square meter are we talking about if it hits that sweet spot? Right, the fluence forecasts give us an idea, and they are pretty sobering. For the really tiny stuff, 100 micrometer particles like fine sand, they predict between 4 to 1 and 10 impacts per square meter might occur during the peak of the debris shower. For millimeter-sized particles, think small grains of rice, the fluence is lower, maybe 1 in 10,000 to 1 in 100 impacts per square meter. Now, impacts of that size could definitely cause damage, degrade solar panels, maybe knock out a sensor, but they probably wouldn't kill a satellite outright or cause it to break up.
Okay, but what about slightly bigger pieces, centimeter-sized, like pebbles?
Ah, yes. For centimeter-sized particles, the fluence is much, much lower, down in the range of 1 in 10 billion to 1 in a million impacts per square meter. So the chance of any single satellite getting hit by a centimeter-sized piece is still quite low, maybe a 10% chance or even less across the entire satellite fleet. But an impact from a centimeter-sized object at these speeds is generally considered catastrophic. It's very likely to be a mission-ending event, potentially causing the satellite to break apart completely, which then creates even more space debris.
So even if the individual probability is low, with thousands of satellites, the overall risk to the whole system isn't negligible at all. It's a numbers game.
Exactly. It's about the cumulative risk across the entire fleet.
Hmm.
And consider this, the rate of impacts during the peak of this event, the instantaneous flux could be 10 to 1,000 times higher than the normal background rate of sporadic meteoroid impacts that satellites usually deal with.
10 to 1,000 times the normal rate.
Yes. So over just a few days, when the bulk of the debris arrives, satellites could experience the equivalent amount of impact exposure that they'd normally accumulate over years, maybe even close to a decade, from the natural background environment.
That's incredible. It's like accelerating the aging process of the entire satellite population dramatically in just 1 week.
That's a good way to put it. And given that huge total exposed area of all the satellites combined, the models suggest it's possible we could see hundreds to thousands of impacts from those millimeter-sized debris particles across the entire fleet during that peak period. While maybe not every hit is fatal, that level of bombardment would absolutely cause accelerated degradation across the board. Shorter satellite lifespans, more malfunctions, potential service disruptions for things like GPS, communications, weather monitoring. The cumulative effect could be quite significant and costly.
And this isn't just a LEO problem, right? What about things further out or closer to the moon itself?
Good point. No, it's not just LEO. Spacecraft actually orbiting the moon, like the planned lunar gateway station for the Artemis program. They'd face an even more severe hazard, being much closer to the impact source. And any future operations on the lunar surface bases, rovers would be in even greater danger from direct high-speed hits. Plus, some of the ejecta gets thrown into longer-lasting Earth orbits, persisting for months or even years. That poses an ongoing, albeit lower-level risk for sensitive platforms. Though interestingly, the study notes that the James Webb Space Telescope way out at the L2 point, isn't really included in this specific risk assessment because its orbit is so different and distant.
Okay, so it's definitely bad news for space hardware. But let's flip back to us down here on Earth. Protected by the atmosphere, yes, but you mentioned a potential show, a sky full of fire.
Potentially, yes. For observers on the ground, assuming you're on the right side of the Earth at night when the debris arrives, this could produce a truly spectacular meteor shower. The number of meteor shooting stars you'd see per hour could be orders of magnitude higher than normal background rates. Way more than even major annual showers like the Perseids or Geminids. You could be seeing dozens, maybe even hundreds per hour at the peak.
But would they look like typical shooting stars, bright flashes, or something different?
That's an interesting point. While the number would be very high, the brightness of individual meteors might actually be a bit muted.
Yeah.
Less dazzling than the best ones you see in typical showers. The reason is their entry speed. They'd be coming in near Earth's escape velocity, which sounds fast, and it is, but it's actually slower than many of the natural meteoroids that create those really bright, intense fireballs. So you might see more of them, but they might appear as slightly softer, maybe slower-moving streaks of light, more like a pervasive celestial drizzle than a fireworks show, perhaps. Still spectacular in its own way, though.
Okay, a potentially different kind of meteor shower. But beyond just watching, would this event be useful for science, like a chance to learn something new?
Oh, absolutely. Scientifically, it would be a potential bonanza, an incredible, unplanned experiment. Think about the sheer amount of material entering the atmosphere. The estimates are between 1,000 and 10,000 tons of lunar material raining down over about a week.
10,000 tons, compared to normal.
Well, the average background input from normal cosmic dust is maybe 10 to 50 tons per day. So this event could dump several orders of magnitude more material in just a week. This sudden, massive influx of relatively low-velocity lunar material hitting the upper atmosphere. It's an unprecedented opportunity to actually sample it. Scientists could, fly high-altitude aircraft or balloons equipped to collect atmospheric dust during that period. And because the influx is so dominated by the lunar impact ejecta, almost any extraterrestrial material they collected during that time would almost certainly be from the moon. It's like getting a free lunar sample return mission, delivered straight to our upper atmosphere, a unique chance to study the composition of the impact site.
A free, if slightly alarming, sample delivery. Got it. But just to double check, we're not expecting actual moon rocks to land, right? No lunar meteorites hitting the ground.
Yeah, probably not. While it makes for great sci-fi, the model suggests the crater formed by this impact wouldn't be large enough to throw out really big chunks, decimeter or meter-sized pieces with enough velocity to reach Earth and survive atmospheric entry. As we said, most of the escape velocity stuff is tiny. It burns up completely. So, while you can never say impossible in space, finding an actual lunar meteorite on the ground from this specific event is considered highly unlikely. No need to wear a helmet outdoors.
Okay, good to know. So this whole chain of events, the asteroid, the potential moon hit, debris cloud, the satellite risk, it really makes you think differently about planetary defense, doesn't it? It feels like the definition needs to expand.
It absolutely does. That's a major point the researchers make. Planetary defense can't just be about stopping asteroids from hitting Earth's surface anymore. It needs to be thought of more broadly, encompassing what they call cislunar space, that whole region between Earth and the moon. Historically, the focus was preventing that catastrophic city-leveling impact on Earth. But this scenario reveals this other kind of threat.
Yeah, because even an impact way out on the moon can generate this cloud of particles that can directly mess with our critical infrastructure and Earth orbit. Our GPS, our communications, weather satellites, maybe even internet access, the things we increasingly depend on.
Precisely. It represents a fundamental shift. We're moving from just protecting the ground to protecting our activities and assets in space as well. Our reliance on cislunar space is growing so fast, our defense posture needs to evolve too. We have to consider these more complex, indirect consequences of cosmic events, not just the direct hits. It's about the resilience of our whole space-based ecosystem.
Which brings up the really big question. If those observations in 2028 make a moon impact look much more likely, especially in that dangerous trailing edge spot, could we actually do something about it? Could we deflect 2024 YR4?
It's a possibility, yes. According to the scientists involved in this research, if the observations in 2028 significantly raise the impact probability, maybe making it seem near certain for that 14% sweet spot, we would likely have enough lead time, about 4 years, to potentially plan and execute a deflection mission. It wouldn't be easy, of course. It would require a major international effort, resources, planning. but the time frame seems potentially feasible based on our current capabilities.
And wasn't there something about this asteroid being similar to the one NASA's DART mission hit? Like, maybe this is a good candidate for trying that again.
That's a really interesting angle.
Yeah.
Yes, asteroid 2024 YR4 is actually about half the diameter and maybe 10% of the mass of Dimorphos, the asteroid that NASA's DART mission successfully slammed into back in 2022. Remember, DART proved that hitting an asteroid with a spacecraft, a kinetic impactor, can indeed change its trajectory. The fact that 2024 YR4 is smaller and less massive than Dimorphos makes it, scientifically, a good target for potentially trying that technique again. It could be another chance to test and refine our deflection methods, gather more data, basically practice planetary defense in a real high-stakes situation, but this time to protect the moon and our satellites, rather than Earth directly.
But there's a catch, right? Trying to nudge an asteroid when it's already so close to the Earth-Moon system. Didn't someone say that could be a little dangerous? What's the risk there?
Yes, there's definitely a note of caution. While DART worked brilliantly way out in deep space, trying to deflect something that's already making a close pass through our neighborhood is trickier. The main worry is precision and unintended consequences. Deflection isn't just brute force, it's a very precise nudge. If the deflection push isn't calculated perfectly, or if the asteroid reacts in an unexpected way, maybe it's less solid than we think, you could potentially make things worse. For instance, a bad deflection could, hypothetically, shift the trajectory just enough to put Earth back into the potential impact path, even if the original threat was only to the moon. Or you could accidentally fragment the asteroid, turning one manageable problem into a swarm of smaller, harder-to-track pieces that could still threaten satellites or even pose some risk to Earth. The closer you are to sensitive areas like Earth and the moon, the smaller the margin for error becomes. So any decision to intervene would have to weigh the risks of acting versus the risks of not acting very, very carefully.
Okay, so wrapping this all up, what's the big picture here? What should we, take away from this potential 2024 YR4 scenario? It really feels like a stark reminder, doesn't it? That space isn't just empty void. Our little neighborhood here is way more interconnected than we usually think. Something happening over there on the moon could have these really surprising, really significant knock-on effects right here, especially for all the technology we now weave into our daily lives. It kind of brings space down to Earth in a weird way.
I think that's exactly right. This deep dive really highlights that as we push further out, as we rely more and more on space, whether it's mega constellations, plans for moon bases, maybe even Mars missions, eventually we absolutely have to broaden our understanding of the potential hazards. It's not just Earth impacts we need to worry about. The universe is dynamic. Stuff hits other stuff all the time. So the big questions become, what new weak points, what vulnerabilities are we creating as we build out our presence in cislunar space? And maybe most importantly, how does our whole strategy for planetary defense need to change and evolve to really protect our future, not just on Earth, but in the increasingly busy space around it? It's about protecting against more than just the direct hit now. It's about understanding and mitigating these complex cascading risks in our cosmic backyard.